Okay, welcome to session number 2. We're going to start looking now into some of the fundamental data structures that are used by the program. And to start out, I'd like to just give some idea as to how these 1,200 modules of TeX can be broken down. Let's see. This is a little diagram that I tried to estimate the relative sizes if you looked inside a memory and took out all the system routines that were needed for running Pascal programs and so on, what TeX would involve. Now the parts here between these lines here, this is code, and then these on the outside are tables of large tables of data. So the program itself has 1,200 roughly 1,200 modules, and I just counted modules, and I'm assuming about 100 bytes per module, 100 bytes of code for every module in the web thing. That's the estimate that I made. So 10 modules would be 1K bytes, and that's 1 square on here. So if I'd say that looked like about 140 of those modules were concerned with syntax, and that accounts for this chart. I also tried in this chart to indicate something about how the parts of the program talk to each other, although it couldn't reflect all the constraints. You get some feeling for the organization of the program by this diagram, so I'll go through it a little bit. There's 3 kinds of input files get read. There's the text, the user's source file on the text input. Then there's the font information, which is here, and then there's the initialization, which is your format file, comes in at the very beginning when TeX is loaded. These are 3 different kinds of files. This one would be a Pascal text file, just characters. This one is a TFM file. And this one is an FMT file. Format file. The TFM file is in 8-bit bytes. The FMT file is in memory words, which is a TeX internal data structure. We would never expect to send FMT files from one computer to another. These are local things that we'd keep only in someone's own local library, and any TeX writes these files. Other versions of TeX read these files. Now the part of TeX that we call its eyes and mouth is the part that reads in the user's text file, and it also has the macros that it looks at for things that have already been defined. The FMT file, of course, feeds into macros. And the syntax part is supposed to make some sense out of these and keep track of what levels of input that we're in, so that we might be reading one file, and then that file said call a macro, and that macro said had some parameter, and we're actually looking at that parameter of the macro, and in that parameter it said input another file, and various levels can be going on all at once. Now remember, these boxes of TeX, I'm indicating just here not the size of the data, but the size of the program. So this is the amount of program I have here to deal with macros, reading and defining macros. This is how much program I have for inputting text from files, roughly speaking. And this includes from the terminal. So this includes things like responding to error messages and so on. But it doesn't indicate the size of the buffers. The size of the buffer is only about half a K. For input. You could make it larger if you wanted to, but it's trivial with respect to the size of the program in that case. Now the alignment is sitting in here too. There's some program for alignment. I said this was the hypnotic suggestion type of thing, and this it sits in the background and contributes to the syntax now and again. Then locals, program to deal with local variables. This is the grouping aspect of TeX. That thing that's supposed to go away when right braces are hit, and we have to save and restore equivalence. The table of local things is called the equivalence table, and this is data here. This is area where we actually are storing all of the counts, the dimensions, skips, the values of baseline, skip, all the parameters, the codes, and also for every control sequence a pointer to where it's defined. Now, after we've read in things, then there's also text out. This can be either the terminal for error messages. It could be to the or to the transcript file or to a send file, and so some program has to be there for dealing with text output, and it's about 40 modules worth. So that's 4 of these squares. Now, semantics is generally what we're doing to digest this information after we've eaten it, and the big part of the semantics is concerned with math formatting. This is everything else besides math, and this is math. So this would be parts for things that do, when you say H-box or something like that, dealing with constructing of boxes, doing proper things with glue. Some of the parsing, though, will be in the syntax. For example, if you say H-skip 5 points, in the syntax we consider the thing that recognizes 5 PT and converts that to a number that the semantics will deal with. Then in the math mode routines, these are the things that will build M lists instead of the semantics. Other semantics build H lists and V lists. M lists are the math lists. H and V are horizontal and vertical lists. Now the programs that deal with the dynamic memory are this is where most of TeX is stored, and so we have to allocate things in this dynamic memory, and that in the first lecture in the afternoon we'll be talking about the dynamic memory. A fair amount of code is devoted to that, including the one I mentioned in the last lecture where it's a display box B, because one of the things you do with the dynamic memory is show what's in it. Then, sort of separate from all that are the optimization routines that come into action after you've gathered together a list, and then we try to break the list in the best way into lines or pages. So there's a paragraph. There's a lot of code devoted to finding the best way to break paragraphs, and that code occasionally talks to the hyphenation part of TeX, but the hyphenation doesn't really talk directly to any other module, just the paragrapher. If paragrapher gets stuck, it calls hyphenator. And the paragrapher puts things back into memory, and asynchronously, whenever there's enough gathered to do something for output, then the page builder comes along and sends something out. Then the program that actually does the output to the DVI file it's not very long. In fact, most of these modules are comments about what DVI files do, what DVI files are. And there's a program that reads in font information, so on. Now the hyphenation tables take up a certain amount of space, and the equivalence table takes up about the same amount of space for all the registers. And we have more space indicated here for font information, and a little bit less for all the strings. And we're going to talk mostly this hour about strings. Now, if you add all this up and say how many K bytes is it, it's very encouraging because it comes out to be something like 260 K or something like that. However, I left out one small detail, and that is there's another table, which is the whole dynamic memory, which I haven't shown on here, because everybody talks to that practically. And you can think of that as an overlay about equal in size, or maybe half the size. So to get the dynamic memory, I would put it. I would say you need 100K of dynamic memory to do a fair amount of typesetting, and with 300K it would be no, 256K is as much as you'll be able to get on some machines with 16-bit addresses, because we address them 4 bytes at a time. So somewhere in between there, you'll get the total size of TeX. I've made these other tables reasonable for fairly large-scale production. So I would say that your TeX would then add up to something between 350 and 600,000 bytes, plus the amount for a Pascal runtime system, depending on how. So for half a megabyte, it looks like you have a chance of doing a good typesetting, but you'd be comfortable with just a little more than that. Any questions on this? I hope this picture helps to give a little bit more perspective as to what we're going to be dealing with inside. So this is a 10 by 12 area from in here, which covers the 1,200 modules in the TeX writing, and the number of those modules devoted to different parts of TeX is sort of indicated by the sizes of those rectangles. Oh, by the way, I forgot to mention, there's little microphones in front of your, and you pick that up and push the red button, and everyone can hear on the tape.
How does that memory requirement compare with TeX80? Do you know offhand?
No, Iñaki, can you say?
Well, about the dynamic memory, the size is about the same, okay?
I think the program has gotten a little smaller, about the same. So, but the string memory is new. Well, I don't know. No, it isn't really new. Things are packed reasonably efficiently. You can also use trickery to decrease the memory requirements, of course, but not just plug in this program. You'd have to do some major changes to some of the macros. There's a wasted byte here and there. I tried to emphasize readability over efficiency without sacrificing efficiency too much. So yeah, but it's roughly the same, I would say. Now let's see. The next thing I want to do is next thing I want to do is turn off the projector so we can see the computer again. I wanted to show you the pool file that Tangle typed out for TeX. We're going to be talking about strings, and one of the things that Pascal is weak on is strings. They provide certain kind of support for strings, but not very much. And so, in order to use Pascal as a language, we had to develop a mechanism. Now, this was originally the idea of, I think, Luis Trapardo and Iñaki in the other version of TeX. After they fought with the problem of strings for one, I think they came up with a solution that's not only good, but has turned out to have many other payoffs that we didn't expect, so that now I'm very happy that Pascal didn't have strings. If I had used Pascal strings, there would have been a lot of other things that wouldn't have worked as well as things are working now. So we have a string method in TeX that also turned out to solve a lot of other problems in a better way than we had than otherwise would have occurred. And as we get more into it, I think you'll understand what I mean. But first of all, let's see what Tangle does to strings. So if the machine is still up, we can take a look at TeX.poo. Can you see this on that screen there? Is it coming up? Oh, it's okay. Now the pool file that's written out by Tangle is it consists of lines again of maximum length of 72 characters because the restriction on the length of strings that you can use in Weave, and each line comes out. Each string comes out on a line by itself. So that means carriage return line feed, or if somebody has a IBM machine, it means that there's a lot of blanks or nulls at the end. Now the first two characters of the line is the length of the string itself. So the first string that currently appears in this program is buffer size, and it's 11 characters long, and so on. You get to see all of the strings if you push through this file, and it's 898 lines long. Actually, the last line is not a string. The last line is special. It's a It's called the string pool sum check. Now Tangle adds this special number with an asterisk in front of it at the end of the file with the following idea, that if you have changed any one of the strings in the program, then chances are very good that this number will be different. And you can also refer to this number in your web program and say, what is my string pool number? And therefore, you can find out if you've read in the string pool that's yours, because you can look and see if your string pool number equals this one at the end of the file. Now, if I edit this TeX pool file, without changing that number at the bottom, this program won't complain. You're not supposed to touch this file yourself. This file is supposed to be made by Tangle. But you see, this is important, because if you started to load a file that was generated without the right, somebody suddenly put another string in his change file or something like that, and your strings get out of sync, then you get very interesting printouts from TeX, where we have some permutation of all the strings coming out. When it says print string 100, it actually prints something quite different, and it might be amusing to some people, but frustrating to others. Okay, so that last thing in the file is the string pool checksum. Now this file isn't that mnemonic to read, because it doesn't tell you what string number n is. And so there's a trivial program at the beginning of the TeXware report, handout that you got, called pool type. And the pool type program does something to string pools, and so we'll demonstrate that now. I think I've got it already compiled. It's such a trivial... wait, my son has a message for me here. Okay. Now, okay, so let's run pool time. Pool file will be tex.pool or poo, and the output will be I don't know, pool. Okay, so now it's reading in that file and presumably making the output file for it. And we can look at pool.type to see, we could print this out, of course, to see what the strings are inside. Now the first 128 strings I mentioned are special. And that's right. These are not. However, the pool type I've done was done with sale versions pool type. So this has our local character set. I'll be talking about character set also in this hour. But let me do another pool type without the sale dependent changes. So let's see. I'll run Tango on pool type without any change file, and it doesn't have a pool of its own. So, and whenever you run a web with it's done. You see, isn't that great when you have a short program? It was 1 second instead of 2 minutes. Now we're going to compile and go. And I'm making a version without the change file. My change file refers to my local character set, and the sale character set has a keyboard that has some symbols on it, which I like very much, especially the unequal sign and the and less than or equal sign, greater or equal than the left arrow. I would find it very difficult to have to write less than greater than every time instead of unequal. That would be quite painful for me. So I'm glad I can do that here. And I imagine there are a few other people that feel the same way. So we try to make TeX that it will be able to allow that for people at Stanford. However, we want to also, so that it's not going to be confusing, that we can also send our files to places elsewhere and not lose the machine dependence. So we have, I think, a pretty good solution to that, and I'll explain it in a minute. First, let's look at pool.temp. Pool.temp shows the strings that we would get without sale character set. So, temp. Okay, now the first 128 strings, so numbers 0 through 127, are what gets printed out for ASCII, for TeX internal codes. And so starting at 32, we have ASCII code. 32 is a space, 33 is exclamation point, 34 is double quote. Can you see that okay? On there, I can't see it on my mouse. Yeah, okay, so and then we get up to 126, which is a tilde, and then the other codes aren't visible in ASCII. And so for interchange purposes, we are representing them with 2 up arrows and another symbol. And for example, 127, which would be ASCII code octal 177, it comes out as up arrow, question mark. And at the beginning of the thing, if you remember, we have the @ sign and A through capital A through capital Z, and then the next ASCII codes that go in there. So this is a form that TeX82 will accept. If you put it in your input, if you say up arrow S, capital S, up arrow capital S, it will treat it as the ASCII code that is 19 in decimal. If I compare this to I'm sorry, it was pool.type. We compare that same thing to the sale character set. You see that at sale, some of these we'll assume that someone can type. So a down arrow will assume they can type. Yeah, that's rather handy for subscripts. And alpha, beta, and sign, not, epsilon, pi, lambda. And then when we get to symbol 9 there, which is octal 11, that's is that tab, I think, isn't it? Yeah, 8 is backspace sometimes, but 9 is tab. And so there, if somebody wants to, so if we're printing out, these strings are used in printing, and so if we're printing out a tab mark that we might have read in at sale, then it would print out as up arrow I. If somebody inputs up arrow I, even at sale or anywhere, it will go in as internal code number 9. Okay, and these tab mark, line feed, vertical tab, carriage return, and page mark, form feed are not visible symbols, so we would print them in that way. And if someone wants to define a control sequence, backslash up arrow L, that'll work, and it'll be a back. Or if he wants to do a checode on that symbol, he can do it this way. Or you can checode your carriage return to mean something, and so on. Now, these internal codes on the other one would all be up arrows. And so if I'm sending a file to some other place, I would use a version of TeX that would print in the standard form. And by making system-dependent changes, you say there's a module called character K can be printed, and that code is duplicated in the pool type program and in the TeX listing module. I forgot to tell you an important thing about how to read web program. That is that there's an index to all the modules. All the module names after the other index, and that's very helpful if you are looking at something in the web file and want to find out where it is in the thing. And as I remember, it was called character K can be printed is the module that I'm looking for here. So on page 438, I found character K cannot be printed is module number 49, and so now I can look at module number 49, and there's a comment there. It's called true in most versions of TeX. character K cannot be printed is true in most versions of TeX. Namely, this is for characters K that are non-ASCII codes, non-visible ASCII code. That's only supposed to work for those values of K less than octal 40, less than 32 decimal. So I'm saying that this is true here. Now, on the other hand, at MIT, I suggest that it can't be printed be 0, 10 to 12, 14, 15, and 33, because 33 is an escape code and 14 is your line form feed, and so on. So then only a few characters cannot be printed in that place. Now this is a system-dependent change, and in foreign countries there will be different ideas on what to do with these codes less than 40. So question occurs: what does it mean? What significance do these internal codes have? Well, in a way, if you changed your codes to anything else, it wouldn't matter that much to TeX. It would still compile. Programs, except that these numbers are used in the language in several ways. First of all, the internal numbers that TeX has go out into your DVI file in the font. Like if you happen to say letter A in a certain font, then the internal code that TeX has for A is what gets used as the character number in your DVI file. So it'll say, so your DVI file say you're maybe in font number 3 and you're setting character number 65. That's a capital A, or at least that's in TeX internal code for capital A. So if the manufacturer has that capital A in another position in his font file, your output driver makes the conversion at that point. So we have to have some kind of standard internal code that everybody uses. And if you're using EBCDIC or something on your external files, the first thing TeX does, reading in a program out of the outside world, is going to convert that to its internal code, so that the rest of TeX knows exactly what's going on, and guarantee that 0 through 9 are consecutive numbers and things like that. Now, if you do something, now you can convert any of your outside codes to any internal codes you want. And then on the output, we'll go back and do the inverse operation. The idea is that if you never print out these codes that are not standard in ASCII, then you can still do it with the up arrow. When I said up arrow S is equivalent to one of these ASCII control codes, I should have been a little more exact. It's not an up arrow. Any character whose code is a superscript mark is the real thing, instead of what I said up arrow. So if up arrow hasn't been coded to superscript mark, then it doesn't work. And if any character who has been coded to superscript mark, the two should be identical and both superscript marks. But they could be any. But otherwise, TeX will allow this on input in the middle of a control sequence name. If that thing is coded in as a letter, for example, it's possible to do that. Now, the other place where internal code is used in code statements, for example, in TeX. So you'll say, what's the code of something, and we have this reverse apostrophe operator that converts a character into TeX internal code number. So code 65 sets the code for uppercase A. The reverse apostrophe uppercase A is equal to 65. So this is a definite part of a language, of TeX language, as to what it does for its internal code number. I think some of you know that SAIL, the computer that we've got here, has a strange code that nobody else does in the world. It's because that they started at Stanford with ASCII code before ASCII code was even in its first form. And one guy, one night, figured he could save 5 resistors or something in our machine by switching around the code of right brace to one to the other. And he did it overnight without telling anybody. And ever since, we've had right brace in the position different from the rest of the world. Now, we have a few other characters that are unusual too, and certainly the burden should not be on the rest of the world, but should be on us to have to make our change file a little harder than yours in order to do that. So TeX internal character code is based on a code that I think is the best proposal for representing these extra characters as in a visible way. It's the one that's used on several MIT machines, so at MIT no conversions are needed if you wanted to use a recommended conventions for codes less than octal 40, the strange ASCII codes. Now, most of you just won't want to do anything with those characters, and you won't see them on your input files, and you won't ever write them on the output files. But you can imagine people in foreign countries that have more than 26 letters in their alphabet, and they also want to have backslash and other control characters to use. I believe it would be a good idea to map those letters for TeX purposes into codes less than 40, and then they can send their source files and everything else to America, and we'll still be able to work with them as if they were generated here. So the internal character set represents these first codes, and then the pool type just types out the other ones with numbers associated with them, so that you can see exactly if you had to debug and you wanted to really look at the Pascal program, and the Pascal program refers to string number 432, then you could look at the thing and say, well, 432 is this such and such a message. So you'd probably be able to recognize from what that string was, maybe a help message or something, be able to recognize what part of a Pascal program you're looking at. So that pool type is simply a help in that way, so that you can figure out what's in one of these pool files that Tangle generates. Any questions on that? Now, what actually happens then when TeX starts? It has to read in the pool file, so it reads in this pool, but only Initech does this. Initech reads in the pool file and checks to see that we've got the right sum check, and stores that all into the format file with the rest of the macros and font information that it's going to preload. On the other hand, it also stores the font sum check, so that the other versions of TeX, they won't check anything except they will check to see that they have the right, the format file was generated from the right sum check. Okay, so other production versions of TeX will also know that their format file is compatible with them. They'll try to load a format file that was generated with a different version of TeX. Then the strings won't be compatible, and so it'll say right away that this format file is wrong. Now the way strings are represented inside of TeX have a big array called the string pool, and let's see where I can. String handling starts in module 36, page 18. Okay. There's a big array declared in module 39, and in this array you see string pool packed array of ASCII code. Now, ASCII code is a subrange of the integers 0 to 127, and only things that are going to go in this string pool array are visible characters that we can print also. So the input routine is set up so that I'm not going to put into that string pool buffer any of the codes that would come out with up arrow something in the printing out. Only the ones that I could print are going in there, and they're all 7 bits characters, nothing over 127 allowed. If you look just above that, it says types in the outer block 18 plus equivalent, and it mentions pool pointer. I guess I should have mentioned that types, when you have the plus equivalent there and it refers to module 18, but here we are in module 38. What we're saying here is that these are more types in the outer block. 18 was the first module where we had types in the outer block, and then if you turn to module 18, it tells you all the other ones where they are. So module 18 says see also sections 25, 38, that's when we're at 96 and so on up to 812. And besides saying where the code is used, it says see also, and this means that many modules with the same name all get butted together in the order in which they appear in the program. So this is one of the places where we want a new type. So when we refer to something as a pool pointer, this will mean an index into the string pool array. And whenever we're talking about the string pool array, then something that's going to go into stir pool, it'll have an index called, the type will be pool pointer. And similarly, a string number is something that's a string start array. Well, the string start array is a directory to the pool. And the strings that TeX gets, once it reads one in, it never removes it again, unless it's the very last one read in. Sometimes the last one read in you don't want to see anymore, and you delete that. But it just operates in a very simple fashion because the rules of TeX turn out that's what you want. So it starts out with all the strings that these 800 and some strings that Tangle give, and we read that into the string pool array. And then after that, we're going to have strings for various other purposes in TeX as TeX gets going. And they'll be continually added at the end, like file names of your fonts and so on. Now, the string start is a pointer into the array, and so that it tells you where that string begins. So string number 100, for example, we'll start it at some place in that pool array, and at the very beginning we're going to put in those first 128 strings also. Even if they're one character long, we're going to put them there. Now there's no string end array. The reason is that if you want to know where string 100 ends, you just look at where string 101 starts, and it's one position, and that's where it is. So we only need the one array, string start, and then we have to keep, if we have n strings in the string pool, we have n plus 1 starting positions. So the start of the string we're going to do next is also recorded there so that we could find the end of the last string we had in. So that's all there's to it as far as representing strings is concerned. And so there's a macro defined there in module 40, length of a string. So if we want to know how long string number k is, we just ask for its length, which is the difference between the two string start positions. So modules 38 and so on just build up very simple routines for dealing with strings that other parts of TeX are going to use as subroutines. There's a simple one that flushes a string, destroys the most recently made string. That's module 44. There's one that's called string room. That's at the bottom of page 18. That string room you'd call string room of 5, for example, to see if there's room for a string of length 5. And so it says if pool pointer plus 5 greater than pool size, then overflow pool size, pool size. The first parameter to overflow is a string saying, you're going to get an error message saying, sorry, TeX capacity is exceeded, and the pool size equals, and then it'll give the numerical size that it's been compiled with. And pool size is a compile time parameter, and all the compile time parameters, I believe, are in module 11. No, module 11, and these that you can decide on as how much space you want. And here I've declared it to be 30,000. Remember, this is a packed array of 7 bits. On our 36-bit computers, that means we get 5 to a word, and 30,000 takes 6,000 words. On a byte-oriented machine, this would mean 30K bytes in a row, and on a 32-bit word machine, this would of course be 4 to word, and so on. This number, it says it must be at least 22,000 more than string vacancies. And string vacancies is another compile time parameter. And I set that to 8,000. Now, why did I put this 22,000? That's because we're using almost 22,000 for the strings in TeX already, the error messages and help messages and everything. I think at the end of the pool type I might even have that. Don't worry about. Oh yeah, you got it. Okay. Wait a minute. I got to go all the way to the end here. Last extension. Yeah, 21,175 characters in all. And so I'm just rounded that up to 22,000 because people will be adding extensions and things like that to probably run it up a little bigger. So this is now what happens is that when it reads in the pool file, it makes sure that there's also room for string vacancies more. Otherwise, any TeX will complain, saying that you've got to increase pool size. So that's a compile time parameter depending on how many things that you're going to do, and it tells you here in module 11. It says it's the maximum number of characters in strings, including all error messages and help text. Also, the names of all fonts, names of all control sequences. These are the kinds of things that go into the pool. You see, it's names of control sequences. So when you declare a control sequence, and it's not a one character control sequence, if it's a multi-letter control sequence, the name goes right into the string pool. Now, here's one of the things I mentioned before, where I was saying that this method of dealing with strings was giving us advantages over what we had in the sale version of TeX, because sale version of TeX we couldn't the implementation of strings was quite inefficient. We didn't want to use sale strings for control sequences. Instead, though, we had to go into our dynamic memory and take away valuable space there for the names of control sequences. My first original design of TeX, if anybody remembers, way back in 1977, I had real strange restrictions. A control sequence had to consist of at most 5 letters, and upper and lower case were not distinguished after the first one, and things like this. It was all so that I could keep a separate table of my control sequences. I had the idea at first that hardly anybody would be defining new control sequences. I didn't realize that macros were going to be very powerful at first, and so then gradually we found that people actually want control sequences. So we've made room for them. Well, now, but treating them as strings solved lots of problems with the data structure, because then because I don't need a special program, for example, to print out the name of a control sequence, because I've already got a program that prints out a string. So that was one of the simple advantages, that we were able to combine two kinds of data structures into one here. Now, you see there are subroutines there on module 45 to compare a string to the buffer. This is what we would be doing when we're looking up to see if our control sequence is in a table or not. Another one that compares 2 strings to see if they're equal to each other. That's what we want to do when we're loading fonts, to see if a font has already been loaded. Then the next few sections are just the things that are used to initialize the strings. One point I could show you at the page 21, module 51. It says, I can't read TeX pool. You notice that that's a Pascal string. It has single quotes around it, not double quotes. You can see why, because we couldn't read the string pool, so we have to use Pascal strings there. Well, now in Pascal you can't call you can't use strings as an argument to a function unless they're a certain length. So you might wonder how I could do this. Well, that's because bad pool, of course, is a macro. It's defined up above there, and it writes this string. And so, again, having macros, we were able to get around one of the deficiencies of Pascal. And it writes an error message saying, I can't read TeX pool, and dies. It returns false to the procedure itself, so that the environment will give you another error message So these messages you have to increase pool size depending on string vacancies and so on are all done in this case. And it also syntax checks the pool file to see if it's been clobbered or not. Okay, any questions on that? I don't see. Yeah, please use the mic.
Can a string begin with a constant?
Can a what?
A string begin with a constant?
A string begin with a constant. A string begins with a double quote and ends with a double quote, and anything goes in between.
Well, I really didn't get you.
Yeah, it's okay. Anything goes in between. Right. So, so any text whatsoever. If you have double quotes inside, you have to have quadruple quotes. You have to double them again, so that a double quote inside of a string gets doubled. In question there?
You said that the string pool is used for macro names, therefore there is no garbage collection if you redefine macro names?
There's no. If it turns out in TeX that you redefine if you define a control sequence, undefine a control sequence, this happens only at the end of a group, then it's very difficult to tell whether that control sequence is really not going to be used again, because another control sequence might have used it and been declared global. And so so there is no garbage collection. The number of times that would actually have saved memory was was actually less than the amount of memory we would have saved by not having the code for garbage collection. So this is why there's no garbage collection. Okay. So the next section talks about online and offline printing, and here's where we get to use the string pool to just print messages. And so I'll talk a little bit about the printing routines. These again are very basic to the whole process. I think these are the ones that actually get declared first. There's a procedure called initialize, and then there's a procedure, then the basic printing procedures, and they start in module 56. The first one is a print line procedure. Now, the interesting thing here is that the printing procedure, there's a destination for printing, so that when my program says print, it might write on the terminal, it might write on the errors transcript file that you get after you run TeX. It might do both. It might be writing on one of the send files. It might be writing into the string pool itself. And so you can change the destination so that all you need is a few print procedures, and whenever you say print integer, that'll send an integer to the proper destination. But that destination might be a variety of different things. You still don't need a different subroutine for each one. Okay, so by switching the destination, we're able to get by with just a few. All our procedures are called print, but what actually happens to it, one of the destinations is no print, which means it just disappears. Okay, and there's one called pseudo, which is number 20. These are all defined on page 22, module 54. This one called pseudo, which is used in an interesting way for showing the context of your error lines. When you get an error message from TeX, it tries to show you where it was, and it gives a two-line indication of this. The first line shows the characters TeX has read so far. Second line shows the things it hasn't even seen yet. And this might be in the middle of a huge macro definition, for example. And so the macro might be 100,000 bytes long when it expands, or very long anyway. Because when we're expanding it, we're expanding all the control sequence names out to their full length and so on. Now, we don't want to have a special buffer that expands out 100,000 bytes and then shows the 60 that we're actually interested in. So instead, we keep a buffer of size 60, and we go circularly around and around in this buffer. That's what pseudo printing is. And then when it stops, it has enough information to just print out the characters you needed in the environment. The buffer is a little more than 60, but it's just a small amount. So this is a method. So pseudo printing is turned on when you have a little bit when you're using this trick of when you're going to run, you're going to print a whole bunch of stuff, and then you're only going to select a little bit out of it. And what you do is you turn off storing into the buffer after you've gotten past your key point. So let's say the buffer is of length 60, and the transition between line 1 and line 2 occurs at a certain point. At this time, you're going to write at most 30 or 40 more characters before you quit, and then you're going to shut off printing. So that's the pseudo thing, which is explained elsewhere. Now that's so by having these print procedures, we can change, but they're all called print, and it's one of the most frequently used things in TeX. We'll say print an integer, and this automatically does binary to decimal conversion, and because you can send the integer anywhere you want, like to a string. So if somebody wants to see a string, but store it as a string, you can do that by setting the selector to new string, and then you get a new string into the string pool. So this is turned out to be another advantage of having the data structures organized this way instead of making use of a particular string feature that might have been in Pascal. So what I guess I'm saying is that by programming my strings homemade, I have much more. I had more flexibility on what I could do with them in an efficient way. I didn't have to worry. I didn't have to consider very inefficient but highly general methods that some system programmer would put in for a string package that would have a lot of overhead, take a lot more memory space, besides making the program a lot more portable and not really longer. So this home-baked approach to strings has not been it turned out one of the first things I struggled with using Pascal turned out afterwards was a blessing in disguise. The print procedure on page 24, module 58, is the thing that we use to print out a string. And so just to reinforce what I've said this hour, I'm getting near the end of the hour, let's just look at that print procedure and see, well, it's so simple it doesn't even call anything else, but just it should reinforce what we're talking about. So procedure print s is integer, print string s. Now this is something I changed last week as I was debugging. S used to be called type stir number, like print new line. S is a stir number, and this is print string at the beginning of a line. It's the same as print, except for the making sure that it goes at the beginning of a line. But here I said s could be any integer. Anybody have an idea why I had to make that change? Why I decided to make that change? The reason is that while I'm debugging, I have made my debugging routines extremely robust, so that if memory has gotten completely clobbered, you're still allowed to look at any location in memory and say, if this is a pointer to a string, print it. And so it should give, and if memory did get clobbered, then at least I would have some, my symbolic indication part of it would make sense, and the clobbered part would be there, but it wouldn't, the program wouldn't die on me. Well, if I didn't say this was an integer, Pascal would stop me, saying that parameter to print is not in the range of a string number. So I change this to an integer, and then we have a test inside the program that says if s is less than 0 or greater than or equal string pointer, then set s to 0. This can't happen. Well, it can't happen unless a bug is present. Of course, everything can happen in a computer if there's a bug. And I don't call an error message if s is less than 0 or s is greater than 0. Remember, I said before, print programs aren't supposed to call error messages. Otherwise, error would call print, and print would call error, and you'd go on and on forever. So it just sets s to 0, which is going to print out a very unusual string. One that the string number 0 is this up arrow at sign. When you see that, that's a good error message enough. Okay, so then J is set to stir start of S. J is now of type pool pointer. It means it's an index into the buffer. I'm assuming that stir start is not clobbered, but the S itself might have been clobbered. Now, while j is less than the string start of the next string, s plus 1, that's always defined. When string s is less than string pointer and greater than 0, then the stir start s plus 1 is defined. That's where the next one starts. So while j is less than that, I print char, string pool j. Print char is the lower level procedure that just takes the character right out of the buffer and sends it out to Pascal, increase j, and continue that prints the thing. So that's why the print char procedure doesn't look for string number. Print char 65 doesn't look for string number 65. Print char prints char, that's TeX internal character code 65. And so the stir pool entries must all be printable characters. Let's look at print char. All of the print procedure, I said you could change the destination. Every print procedure works through print line and print char. These are and they all reduce to these. So these are the only two that look at the selector, that look at the print selector and so you could if you want to deflect it, you just deflect it in these two places. And print char takes an ASCII code as a parameter, and so for example, let's suppose we're writing on the terminal only. That would be term only case, and it would say write term out xchur of C. Now xchur is the array that is set up to convert from TeX internal code to EBCDIC or whatever, and that's where you want to make system-dependent changes. So let's look at where xchur is set up. That starts on page 10 in a section called the character set. And the things I mentioned about character set are discussed there on page 10. On page 11, you see where xchur is set up, a whole bunch of assignment statements. These are supposedly not system-dependent. If we assume that your Pascal can read any of the visible ASCII codes, then you don't need any changes here. Otherwise, you do. But these assignment statements will set xchur of octal 40 to the character blank and so on. And many implementations of Pascal will then set xchur properly by these statements. Then on the other codes less than octal 40, that's explained on the next page, on page 12. And there's and the standard version of TeX that hasn't been modified in module 23, the standard version down here says just blank it out. Set all these other characters that you don't expect to find on the input to blank. And then, if you ever want to output them, they'll output as blanks also. But at MIT, I suggested that you could just set them all to the character itself, because TeX internal code agrees with this MIT code. So that's a system-dependent change that, of course, would have to be made if you want to do something special with the codes under 40. However, most installations won't have to do anything with those, I guess. All right, that's all, except if there are questions. Any more questions? I can offer you a tempting lunch if you don't ask me any questions. Okay, good. That works. So we'll meet again here at 2 o'clock sharp. Thanks, Vic.